All right, on the air. Although probably on the air with nobody. Yes, 0 viewers, but we'll see.
Can you see that?
Okay, so for those of you that are new, thanks for coming out. This is the San Diego Tech Immersion Group. We are contemplating changing it to just the Tech Immersion Group and dropping the San Diego and getting more people on the online stream. There seems to be some interest from outside of San Diego. People want to jump in and listen. So for those of you that have never been, we'll give you just a quick overview of the group and why we started it and what the point was. I'm Brad Cunningham, myself, and Ike Ellis, who's not here tonight, and Scott Reed, who will be showing up at some point tonight. The three of us were years ago, maybe 6 years ago or so, we were doing nerd dinners. I started a nerd dinner thing, which was just like, let's go hang out and have beers and go to nerd dinner somewhere. And there's about 4 or 5 of us, and we started talking. We realized that the conversations we had there were really interesting, and we're getting more value out of those than the typical user group. And so we thought, why can't we translate this into a different style of user group? So we wanted something where you get a little more meat on a topic, where it wasn't just stand up there and listen to a 20 minutes, 30 minutes about somebody giving you a high level on a thing, on a topic, and you could have just Googled that yourself. And so instead, we thought, let's do this immersion kind of style where we pick a topic and we stick with it for 3 or 4 or 6 or 8 months, and we pick a book and we pick a series of mentors. And then everybody will read along with us and will learn with us and ask questions with us. And a lot of times the topics are not things that we're experts at. Perfect case in point, Python. None of the people, myself, Scott, or Ike, none of us really knew Python. Scott Reed knew it, but not to the level that we've learned it ourselves during this period of time. And for this series of Python, this is the 3rd chunk in the Python track. We started with Python the language, and we just kind of went over what Python is as a language. We spent maybe 3 months on that. And then we talked about Python in the context of web development. And so using Python as the backend code for your web applications. And then we took a break for the holidays. So we've been off for 2 months. And now we're starting Python in the context of data science, data analysis, and really a heavy focus tonight, at least, on machine learning. And that's a topic that none of us knew. So we invited Chris Lucian to help us out. Chris is the director of software at a local company here, and also did your master's thesis, right? In data science, data analysis, and did it in Python. So he's kind of the expert on the topic. Speaking of the devil, there's Scott Reed. He just walked in. So Scott, say hello.
Hi.
So we're really excited for this topic. For those of you that have been with us a long time, I know a few of you have been to many of our meetings. It's probably only the 2nd or 3rd time that we've had a legitimate guest mentor. We've convinced someone outside of our group to come and teach with us. So we're really excited. Usually it's myself or Scott, right? But we've done a lot of topics. We've done Entity Framework, we've done WPF, we've done T-SQL, we've done cross-platform mobile development, C#, HTML, JavaScript a couple of times, CSS. And for those of you who've been around a long time, we've done a lot of topics before. So our plan for the next couple months is to finish up the Python track, to do this data analysis section, this machine learning section. Chris is going to lead us through there. And then after that, we're going to switch to a totally new topic, which we haven't even picked yet. The current leading candidate from last time we took a poll was DevOps. So it was Docker and continuous deployment and that kind of tool chain, build servers, CI, that sort of thing. So that's kind of still at the top of our list. We'll probably take a vote at the last meeting of the Python of this section. We'll probably take another vote, see if anybody's changed their mind, if the world has changed since 6-8 months ago when we took that vote. But that's our plan. We highly encourage discussion here, so please ask your questions. We've got people on live stream too. I don't know if anyone's ever listening yet, but
people are there.
People that are remote, there should be a chat there on YouTube. You can chat, and we'll try to monitor that as best as possible. We know that the live stream is delayed by about 1.5 minutes, so there might be a little bit of interruption as we answer those questions. But we want you to discuss, like I said, for us, myself and Scott, I think we're learning this topic as well. We don't really know. It's going to be up to Chris, so we're probably going to jump in with questions as well. The point is for everyone to learn. So, no stupid questions. That's the whole reason of this group. Ask your questions, either topics you may know nothing about. You may know nothing about Python at all. This might be your first exposure to Python. Just jump in and ask the question. I think that's about it. I don't know, Scott, if you got anything else to add about what TIG's all about. We started it. Good stuff. All right.
We can virtually guarantee that there will be stupid answers, though.
Oh, yeah, absolutely. That is one thing. Yeah,
there will be an argument.
Yes, there are 2 things that are true about TIG. That we will always give dumb answers, and we will always argue about said dumb answers. I think we did it once because that's just our personality. We can never agree with each other, and so we just argue. And then people came up to us after the meetings that was the best part of the meeting. Just keep arguing with each other. So inevitably that will happen, but that's not how you do it. And, and people get a lot out of that. So, so it's Nerd Book Club. You get to hang out with us, eat pizza, and argue with us, basically. That's the gist of it. Any questions on TIG in general before we get started? I know a couple people are new. They said they've heard about it on Meetup. Anybody else? Is this their first time? Where'd you hear about us? Was it Meetup? Yeah.
It's my first time.
Cool.
I've been aware of your group for like a year and a half. I go to the .NET user group.
Oh. You've just been stalking us, waiting.
Wednesday nights have always been impossible for me to my schedule, but I had schedule changed.
Nice.
As chance would have it, this is right up my alley. I've been studying machine learning and Python for the last year and a half or so.
Sweet.
Just in my spare time.
You wanna take a seat there?
Yeah, come on down.
I'm hardly an expert, but at least I'm hoping I know enough so I can get
Great. Yeah, hopefully you contribute a lot out of it too, right? Because I think it is a new topic for a lot of people, so hopefully we can get some good discussion. And you're new as well?
Yes.
Yeah. And where'd you hear about us?
Meetup.
Meetup. Awesome. Cool. Well, thank you all for coming. And Chris, it's all you. Take it away.
All right. So I just want to talk a little bit about myself, just to say where I'm coming from. I did my master's thesis in computer vision using machine learning. So a lot of this statistical analysis and basically the idea there was to be able to do facial recognition from different angles and different positions and different distances. And so it was a great learning experience. And during that time, I did experiments with bioinformatics and HIV-related drug synthesis using machine learning, and some other just kind of one-off things. So a lot of which came from the UCI machine learning database, where we were predicting wine tasting and diabetes in patients and things along those lines. So machine learning has a very wide variety of ways to go about it. Also, I want to talk a little bit about the book that was selected. So I had originally talked to Brad and brought forward another book, but it's one, it's a lot more expensive, and two, it goes way too deep into the statistical part of things. And this book does that less so and is more of a practical uses sort of thing. And so
We have the book. You pulled it up.
I got one right here.
Machine learning and Python.
Yeah.
It's on the Meetup group. If you didn't already get it.
So yeah, it's got a few links in it, and I kind of want to take everybody through picking up everything that you'll need to use it. So just having PyCharm and the default installation, you'll have a hard time setting up the environment, but they have a very easy way in the book of doing it. So I went ahead and got those links and put them up on the Meetup.
So if you're new to Python, by the way, for this is your first meeting, PyCharm is a free Python editor from a company called JetBrains. So we've been using it in all of the Python meetings. That's just the editor that we write Python. You can obviously write Python if you want, but PyCharm seems to work pretty well, and the community edition is a free download. So PyCharm.
Yeah, if you go to discussion here, and then the post that I made earlier, you can kind of see PyCharm Community Edition. It's a free editor from JetBrains, really awesome refactoring tools and things like that. Then Python Anaconda is the special piece that they want you to download for this. Anaconda is a distribution of Python that has all of the data science stuff packaged in. And so rather than relying on pip to install all the tools that you need, you can just get Anaconda. They'll have them all there for you. And pip doesn't understand all the interdependencies for these. Some of these projects are maintained in a different way or have modified the configuration of Python internally. And so getting Anaconda will get you set up to just run these and go. So I was having a hard time building it just using a standard distribution of Python and using pip to download everything. And so instead, the book said to go get Anaconda.
Now, I noticed you say get Anaconda version 2, not 3.
Yeah, so let's go look at that site real quick.
What if you're using version 3 of Python?
So each of your instances of Python, and I'll show how to set it up in the editor, but each of the instances of Python are kind of packaged in its own folder. And no matter how many path variables you have for that version of Python, you could have you'll see on my machine, I have 4 or 5 different versions of Python on my machine. And so each of them have their own packages and each of it. So that's just the distribution of Python that you have. And so they've been packaging Anaconda in version 2.7 and version 3.5. But many of the data science tools haven't been converted to 3 yet, like we were talking about in the beginning of the group. So many of the more commonly used tool sets have been converted, but a lot of the data science systems have been reluctant to convert over or don't have enough community activity to convert over. So this book, I believe, was using 2.7, and I was able to, just by downloading this version of it, set it up. And I'll show you how to set it up in
I have a
Python.
dumb question.
Yes.
What tools have not yet been ported to Python 3.5 right now?
I haven't looked at it. I'm going off the book for that, but yeah.
I have another dumb question.
Mhm.
So when we originally started Python, the language talk months ago, you had actually mentioned in that meeting that, I'm going to screw this up, out of the box, Python is interpreted, the like installed Python is interpreter, but there are compiled versions of Python that use a C compiler or something along those lines.
Yeah.
Is that roughly right? Is Anaconda doing that?
No, well, it's so there was two things that came up. So one of them was actually turning a Python program into an executable or a Microsoft app. Those are actually packages called Py to exe or Py to app. Those are other things. But what I was mentioning about machine learning back then was many of the Python just hooks into other languages. So many of these systems are written in C++ or C or something else, and then they have a Python wrapper, and then you can pull in things that were written in different languages. So you might be using a tool that was written in C#, another tool that was written in C++, another tool that was written in some other language, and it will pull all of them together and make them all accessible to you in one place. And that's kind of one of the beauties and scary parts of Python. So
out of the box, I just install Python, I write a Python program.
Yeah.
I can ship it to anybody, assuming they have the Python interpreter, they can run my document.
yeah, assuming they have the proper distribution of Python or the proper packages installed. But the nice thing about, and I can kind of show it here. Right now, my project interpreter is set to Anaconda, but as soon as I go off of Anaconda, this is something that you'll have to do if you have multiple versions of Python installed, is search for interpreter in the settings. Project interpreter, right? So this guy right here shows you, so that's all the different versions of Python I have on my computer. I have a standard Python 2.7 installation. I have Anaconda 2, which is the 2.7 distribution of Anaconda. I have Python 3, 2 versions of Python 3.3, a version of Python 3.4, and a version of Python 3.5. And these are all different configurations. And you'll notice, like, this is the set of packages. That list there is the set of packages that I have. So if I jump to Python 3.5, you'll see that I have actually a very minimal set of Python. And if you ever need to install something out of Python, you can just double click on one of these, get the available packages. And this is actually making a call to pip. And so right now I could look for pandas, right? And pandas is one of the things that I need to run something over here. And so if I hit install package, it goes out to the internet. You can kind of see this little loading bar at the bottom, right? It's going out to pip and installing it, kind of like a NuGet package. Thank you, Jim, and Scott. Yes.
You should point out that Anaconda also has its own package manager that guarantees that everything stays up to date. So if it finds a dependency, it loads that. If it finds an update.
Yeah, and pip is supposed to do that for you, but you can see that I got a failure here. And this is kind of what I want to show. So it's not, it doesn't understand as well. And Anaconda, they have a large number of packages prepackaged, or bundles prepackaged. So
Is Anaconda using, what's that isolation thing in Python? I forget the name. Like
Virtual and
yeah, virtual env. Is it using virtual env to firewall the Anaconda world?
I don't know.
No, it
But,
replaces it.
Anaconda replaces.
Yes, they have their own environments.
Yeah, there are other distributions that have a lot of these tools. So there's another one called Canopy, also, that has that actually they ship their own IDE with it, but you can still hook into it from other interpreters. So, but you can kind of see that right now, my installation of PyCharm can recognize that I have these distributions of Python. And if you convert it to an app or something like that, you won't be able to get into that set of packages. So
when you were saying about different languages, if you're in the Anaconda project interpreter, some of those packages might have been written in C or or something else.
For example, NumPy is one of the packages that we'll be using, and one of its big strengths is to be able to process large grid data sets or hyperdimensional data sets, and you can do a lot of different matrix math operations on it very fast. A scripted language would never be able to calculate those things quickly enough. So what they do is they hook into C++ or C or whatever they wrote it in, and they run all of the computation and then they spit it back out at you. And so that's why a lot of, I believe the API for the D-Wave quantum computer is also written in Python, just because you can hook into the other things. You don't need to care what things were written in and things like that. So. Yeah, so the book says that Anaconda will make your life a lot easier. I tested it out. Anaconda will make your life a lot easier. So I did double check and I did look and see what.
I'm going with 3.
You're gonna go with 3? You're gonna try 3?
Absolutely.
You know, I didn't download it, but you could, yeah, go ahead and try it and see what it does. I mean, it might all be there, but one great way to just search for whether or not. So in the other book, the original book that I was going to recommend, none of the code examples would work in 3, and the reason was that all the he had a bunch of print statements in there, and the print statements weren't using parentheses. And so
as we learned last time, there is a
converter
223 or something like that. Script on your 2 scripts, and it will fix 99.9%, as they say. That's not me. They say it will fix 99.9% of all conversion problems.
I think 3 comes before 2.7. Right?
3? No, 3 came after. But so the thing, and we were discussing this in the first set. But
wait, no.
What?
You're right.
There's still
3.
Oh yes. Yeah.
Came before
3.0.
2.7.
Yeah. But now, 3.5 is after.
Yeah, 3.5.
Yeah.
But they have stopped 2 dot development, or is that like 2 dot
Hot fixes only.
No.
Yeah, a lot of people are still heavily dependent on 2 point stuff.
Okay.
So that's why they're doing hot fixes or security updates or whatever. So yeah.
On Amazon, when I read the reviews of the book, the book is very good, explaining the fundamentals, but they complain about the examples.
Yeah, so I noticed that too, and one thing that they don't really take advantage of in the examples is they don't use slicing efficiently. So he uses slicing, a light version of slicing in here, but some of these examples, they just loop through items and things like that. And so some of the code examples aren't very good, but the nice thing about the book that I liked was that what it covered was more of practical uses rather than statistical theory and statistical mathematics. So those are the kind of areas that, if you wanted a deeper dive, the book by Stephen Marsland is a really good, in that book, he writes a neural network from the ground up in Python using NumPy, and it's quite interesting. It's good, and if you really want a deeper dive, it's a good book, but it's like $80. So I that's what I used for my class, one of my classes when I was
studying. We'll post links to the other book on Meetup and the code sample, like Chris was doing some stuff off the cuff coding. We'll post that on his GitHub. It'll be publicly accessible. For those of you on the stream, just if you're not already joining the Meetup, and you'll get the data there, so that after this meeting you can look at all the examples and that sort of thing.
Yeah.
Another stupid question.
No problem.
We're the only ones allowed to ask.
Yeah.
Run it through you. When I was running, I'm running Python 3.4, I think, maybe 3.5.
Mm-hmm.
And that, of course, comes with its own virtual environment. And when you set up a virtual environment and try and run, I don't think PyCharm had, no, it was through PyCharm. Under Windows, apparently not all the paths get set properly, so I couldn't get stuff to run because it's not looking in the right places.
Yeah.
And I'm wondering if you run into the same issues with Anaconda.
So it depends on if you run the installer or not, because usually the installer properly treats your path. But if you got a zip of a distribution of Python and put it somewhere, then your path variables aren't set. And so you can either set your environment variables to point to the appropriate locations, which is how my version.
Well, it's not just my global environment variables, because if I run it outside of PyCharm, it's fine. If I run it out, it's running it in PyCharm that has the problem.
So you're probably not you haven't set this window up correctly, is probably what's going on.
Okay.
And so what you need to do is make sure that you have you go to add local and you find the python.exe for the version that you want. And once you set it in here and select it, it changes it for the whole project. So now anytime you say you right click a script and run, it will run it for the proper installation of Python that you have.
So that's selecting a global environment though.
Yeah, and so alternatively, you can go in and set per script environments or something along those lines where you say edit configuration, and you can change the project interpreter here. So if you wanted to say run it on 3 different versions of Python with the same script, you could just go in here, name that configuration, and you set the individual project interpreters for each of those.
So she's probably opening a 3.5 project with 2.7 as the interpreter.
Possibly, if you have a second distribution of Python on your machine and you have the wrong one. Oh, okay. Yeah, I mean, maybe.
There could be another option, if you set up a virtual environment and you haven't, whatever it is, sourced it on Mac. But,
I did Google the problem, and they said it was a known problem under Windows, and that you needed to change some settings in I don't even remember where it was, some sort of initialization files, but I couldn't get it to work that way.
Yeah,
bring in your laptop.
Yeah, bring it into the next meeting and try and hack away at
Hit
it.
it with a hammer for a while. Brad is a hammer. Just let Brad at the problem. Give me your laptop.
Yeah. So let's go back to the links. So one more thing, the source code, you can just download it. I have it downloaded right now. It's by chapter. So chapter 2 is the first one that starts with code. So what I did is I downloaded it, then I opened the folder, and it's just 2.0. And so you see, like, I'm in downloads 2.0, 2.02. And I just unzipped it, opened it up, and now I can go to any one of these, and I can right click, oops, don't debug, run. Takes a little while. Some of these examples are computationally expensive, so I think I'm debugging that. Hang on, let me try this one more time. There you go. So this is the pie plot that came out, and you'll kind of see, whoops, you'll see the plots get spit out of this. So this is actually a correlation matrix from one of the examples. So you'll get a lot of pretty graphics out of this, data visualizations and things like that. Also, and PyPlot is one of the main tools that people use to create some of the data visualizations that you see when working in Python. But so each of these typically have some sort of plot associated with them. When you run them, it runs against the data. You can graph all kinds of stuff with this. So it's a really powerful tool, and we'll be learning to use that too with this book. So these are some of the more heavily used tools in machine learning. In that
Did you call it PyPy or PyPly?
PyPlot, or
PyPlot.
Yeah, so PyPlot, and it's from matplotlib. So
Pitplot.
Yeah, Pitplot. Pitplot.
So,
Yeah.
if I may, I sort of hate to introduce this, but just because people at work would yell at me, there is a statistics language called R.
Yeah.
That makes a lot of this just trivial.
Mm-hmm.
And it's a horrible language. I hate it. But I do have to say that, for instance, graphic, you can do the most beautiful plots.
Yeah.
And they have this really nice system called ggplot.
Mm-hmm.
And
So
statisticians really come to love it because it's got everything and it does it all for you.
Mm-hmm.
As long as you can figure out how to ask it how to do it.
yeah, and that's a big part of it, and I kind of like made a little PowerPoint just to keep talking points available, but I talk about like what is data science. Well, data science is basically another word for a statistician, right? And when you talk about science in general, you're talking about the scientific method and running an experiment. And so a reason why R is very popular is because they're trying to run experiments and create theories about the data based on a hypothesis, right? And so that is great, but also you run into the situation where you want to use that information now practically, and you want to start using that in real-time systems or something along those lines. And that's where the line kind of gets blurred when you're using R, because it's hard to integrate it into, say, a website or something along those lines. Or you can have everything kind of in the same language, or you're operating off of it. So R and Python are kind of both really advanced languages for machine learning. The benefit to having Python in general, I think, is that it's one of the more used languages out there now. And it's a
general programming language as opposed to a specific programming language.
Exactly. And so R has that kind of fallback. So one of the classes in machine learning that I had a long time ago, we were doing different experiments and comparing results with each other. And one of the students used R, and others used Python, and others used other stuff. And so, because you can do the same stuff in C# too, but C# makes it incredibly difficult to manage the data compared to R or even Python. So that's why there are libraries like Pandas and NumPy, is to simulate that ease of manipulation of data that R can get. So, but I agree with you. Like R is something, if you were really heavily into this and you were creating theories about data and running experiments like that, then R might be a better language for you than Python would be. But if you're trying to incorporate it into a website quickly, that's, it's going to be much more difficult to incorporate an R system into a website than it is.
So Jason would just be upset if I didn't also mention
F#. Yeah, there you go. Where's Jason?
Jason. There you go.
You didn't say his name in the same sentence.
Yeah,
so
you can do all this in F# too, and there is, in my experience, there's a specific avenue of financial data analysis that happens in F#. There's a lot of finance programmers in New York that use F#. I get called all the time by recruiters saying, "You know F#? We've got this trading platform in New York on the stock exchange written in F#." There's lots of people using it for
and that's growing in private
processing.
But it sounds like Python's being used for the financial,
Yeah.
kind of like, for example.
Yeah.
It is. I mean, it is widely used, and you'll kind of see why. Cause one of the big things about Python is that it makes it very easy to hook into. So another one of the libraries that we'll be using is sklearn. And
sorry, we have a dance studio next door.
Yeah. So this is a great image right here, but this is kind of 3 different data sets and different models used against those data sets. They all share the same interface, and basically you can hook into sklearn and try and run different experiments on the same set of data multiple times with different data sets using the same interface, and it's really fast to just go in and try different things and work with it. So that's sklearn is a big reason why a lot of people use this system and quickly get into it. So, and I'll use this image more as we go. Let's see here. Where was I? We were still on links. So finally, machine learning database. So we kind of talked about this during the intro YouTube. UCI has a great database of data sets that are made available. And so here's the wine tasting set that I was talking about. So you can just go here and use the data. And the great thing about this is that a lot of people have written papers about this. These are all papers written about the wine data set. And so these are all academic papers published, and you can look up through academia and stuff like that. So this is all real.
Nice light reading.
Yeah, some nice light reading for you about how to predict wine tasting results. So you can always just go into the data folder here pick up the data, and this is the data. And then if you need an explanation of what the data is, you can go into the names file. So these are really easy to get to. They're really easy to load into by, through pandas and NumPy, and then start working with an sklearn, and you can actually run experiments and prove things about the data, about basically relationships that exist within the data that you wouldn't have originally known about. And so that's kind of where we get into the data analysis portion of it. You can tell a machine learning algorithm typically to remove irrelevant columns and things along those lines. And what happens when out of that is that you can actually find out which pieces of data are irrelevant to the prediction, and that also can be used in data analysis and things along those lines. So
this is nice, because this is probably one of the biggest hurdles to really, when you're learning data analysis, really doing this well, is finding large data sets of data that is good and useful. And it's not. I think I mentioned on YouTube, but and I looked up afterwards, the one that I remember from years ago was Netflix. They did a challenge and they dumped anonymized data, and they said, can anybody improve our recommendation engine for what these people should watch after they watch this movie? I went back and looked, and somebody did win it, and it was $1 million prize. At the time, Netflix paid a team of research. It was a research team at a college that won the thing, and they got $1 million. They beat Netflix statistical algorithm. They had a statistical number. They said, you can get better than this mean average on recommendations. We'll give you $1 million. And at that time, 2007 or something, that was like the biggest data set that I can find freely available, other than this, which is temperature data mostly, or
There's a lot of stuff on data.gov actually. It's not always the most usable. The UCI site is nice because it's usually just flat text files, and maybe you need to remove the quotes or something to get it into the exact format that you want it. Sometimes the data.gov stuff is like an Excel file, and you have to do more parsing to get it to be usable. But there's actually all kinds of data on there, the agricultural stuff, data about food stamp usage.
There's a lot of crime statistics on there too. Different cities, police departments produce crime stats for your neighborhood or whatever. If you want to know.
Or if you don't want to know.
Or if you don't want to or if you want to look at somebody else's neighborhood. I think weather is the most common. I think weather.gov and NASA, I think, and countries around the world I know have weather monitoring. They're IoT devices. They have weather monitoring things out in the wild and the oceans and on land that are getting surface air temperature and tides and stuff. And those are just producing massive amounts of data that most of the time that's publicly available somewhere on the internet if you look long enough.
Okay, so whoops, no, hopefully I didn't click that. All right, so kind of moving forward. So we have the scientific method, we have experiments. So that's kind of how we want to evaluate how well we're doing with performing predictions, and then we use the results of those predictions to perform analyses and things along those lines to kind of get the data science umbrella. And so we'll look at visualizations. We'll talk about big data. The book in the first chapter kind of talks a little bit about big data versus small data and things that you can do. So there's certain algorithms that are computationally expensive that you can run on small data sets and get better insight into. And then there's big data, and you can run simpler algorithms that can give you insights into larger trends and things along those lines. So those are the big things. And then there's a system called stratified sampling, where you can take big data and turn it as best you can into small data and operate on it too. So there's all kinds of ways to do that. And I would want to kind of keep a focus on practical use or just running experiments without getting too deep into the statistics portion of it, because that's a whole other topic and that can actually last a really long time. So machine learning, statistical models, time series analysis. So before I did any machine learning, one of the things that the professor that worked with me on this was, and when I first started learning, is that before machine learning, before these processes or before statistical processes like this, they use time series analysis. And so the first thing that I did was start with the ARIMA model. And the ARIMA model is a statistical tool that allows you to take a year's worth of data and incorporate yearly and monthly trends, or multi-year data and incorporate yearly and monthly trends. And what ARIMA does is allows you to remove noise that that carries across multiple years and make more accurate predictions based on that stuff. So that's just an equation that people use, and it's used very commonly in financial stuff even today. So I just wanted to throw that out there. I don't think we'll do too much with it, but it kind of all stemmed off of these simple function sort of based things and stemmed out.
One as an example of like the type of noise would be something like on the news, you'll often hear something like seasonally adjusted sales, right?
Yeah.
Because I don't know, like people don't like to move at Christmas, so home sales are down, right? That's known. It's not really an indicator of anything going on with the housing market.
So here's a great example of ways to remove kind of global, local, or yearly or monthly trends. And so you can kind of see here that there's an overall linear trend upward and things along those lines. ARIMA will be able to make predictions based on all the historic data to continue this graph going on, as long as it has data to tell it enough about the increasing. So these are examples of data sets that you'd use the ARIMA model on. Yeah, so to throw that out there.
Let me ask a generic theory question, like just in data analysis or data science in general. One thing we were talking about kind of offline is that a lot of this is not that there's a right answer, or even that the most accurate answer is the right answer, right? Accuracy doesn't always correlate to correctness in this case. So how well are these, like I don't know how to phrase this question, but how well are these algorithms used to answer questions that don't clearly have an answer? I don't know if that makes sense. Like, I'm just thinking like polling data. Who's going to win the election? Like, that's a complete crapshoot if you really think about it, right? But how accurate would they use these sorts of data analysis models to try to grab and pull the data over multiple years and filter out noise? Did they really get close? I mean, I don't know.
It really depends. So so one of the things, so kind of starting with the accuracy portion of it. So you want to definitely incorporate false negatives and false positives into whether or not your accuracy is worth anything to you. And so for some people, a false positive is extremely like a really bad thing. Like, do I give away my position to destroy a tank on a false positive? And so you'd be very reserved in that case. Or a false negative is, is that a tank? Oh, it wasn't, and the thing over there is, right? And so so a lot of the time, and I'll get into that a lot more. So there different models and different forms of measurement will give you basically different outcomes to what you're trying to predict. So that's part of your question. The other part is these models used for elections and stuff. So there are people that very accurately predict horse races using these systems, but no one can make 100% correct March Madness bracket. To use something that you'd understand, Brett.
Now, horse race is a perfect example, right? Like, it's a complete luck of the draw. They'll never get 100% right, but maybe there's some value in the data.
There are values in the data that get machine learning can predict readily and accurately.
I mean, stock trading, right? So
yeah, stock trading is totally. It's
analyzed to death.
Well,
so
if these real-time trading systems are making trades at faster than human possible speeds, therefore,
and that's the thing, is that anything that you measure is, it can be gamed. Well, the computer's trying to game it, but the computer's also measuring it, and other people's computers are measuring it. And so what happens is there was a stock crash based on machine learning. I forget what year it was, but all of a sudden, all the machine learning systems started selling everything. And it wasn't that long ago.
There was a couple of them. So that's why I'm laughing. Because you said there was
machine learning.
A stock crash. No, there's more than one.
Yeah.
They just stopped trading. They have fail-safes in, they dropped the bottom, fell out, and they stopped trading.
Yeah. So predicts stock crashes, stock forecasting.
Instituted safety gaps after that because it was
so they
took over and sold up.
Yeah.
China just had it like a week ago. China's market fell out, the bottom fell out. like people, it was a sell-off. Like somebody triggered it and all the machines were like, holy crap, and started selling.
Yeah.
Shut the market down because they lost 20% value in like 2 months or something.
And so
Because
White
one
color.
machine figured out that all the other machines would
Right.
sell.
So they were gaming.
yeah, they're okay.
The humans were standing back while the economy crashed.
Yeah.
That sounds
And
like
so-
fun. Let's not do that.
So
Let's
the,
just play tic-tac-toe.
Yeah.
So
And
that-
predict the outcome.
yeah.
Would you like to play?
Only if it's a tank.
And so that kind of lends to my previous argument. It's like, is accuracy really what you want? And the answer traditionally is no. You don't want. So a high accuracy is great, but you can do something called overfitting the model. And overfitting the model, the idea is that you've predicted so close to the data that you have actually no room for outliers. And so as soon as you hit an outlier, your algorithm doesn't have a margin of error to like say it's going to be like 99% sure that it's not a proper prediction. That outlier will come out and then you'll get hammered for it.
It's like saying there's 100% certainty that this data is not data that I've seen before.
Yeah.
I would like to have another take on Brad's question. I think it's very big in absolute terms, like, is it any good? And it should be, I think it should be kind of, we should look at it in relevant terms. So for example, you're giving out loans. Some loans will not get returned. That's the truth of life. But if you make 1% better decisions, which loans you give and which loans you deny, you will get more money. So it is like that. The machine learning system will give you probabilities on horses, and if you have a better system, it will give you higher probabilities on winners. You get more money. You're happy.
But it's not. So the horse examples, it's more like what you said. But the loan example, your first example, there's two ways to make money, right? One is to make 1% of better loans that people actually pay back, and two is to make the process of making that decision cheaper, right? So if you just have a machine learning model that can decide whether or not to give you the loan, then you don't have to have a banker with a salary to make that decision, right?
Right, so in that case, it doesn't have to be any more accurate. It's just cheaper.
If it's just as good and can do the job the human does, then it's worth doing.
So this is kind of
Long live the machines.
long live the machine.
Still try to unplug them.
Yeah. That's the whole thing. If you have a chess game that doesn't want to be unplugged, take over the world. Yeah. So when you see AOC or AUC instead of accuracy, we're talking about the area under the ROC curve. ROC stands for radar operator characteristic, receiver operator characteristic. That's it. Yeah. So what it is during World War II, the analysis of whether something's a tank or not had false positives and false negatives. And so you basically, when you had a false positive, that was really bad. When you had a false negative, it was really bad. So you wanted to be very cautious on what you want to do. So if you increase your false positive rate, what's your curve, and if you increase your true positive rate, and what happens is everything underneath the curve set here, this area is kind of your measurement for success, because now you can fine tune, well, if I can get my false positives, all the way to 0, but have only a 70% prediction, then I'm willing to take the hit of the 30% predictions when I get, instead of having more false positives. So I don't know if that makes really any sense. It took me a while to get this concept actually, but the idea is
you don't want to blow up something that's not a tank.
Yeah.
Right. That would be a false positive.
And that gives you away. It gives away your position, right?
And it gives away your position. So you want that to be 0.
Yeah.
And the trade-off would be that
Miss
you
some
get
tanks.
miss some tanks.
But you didn't give away your position, so hopefully those tanks didn't blow you up.
Yeah, exactly.
That's
exactly.
a better trade-off than accidentally blowing up the hospital.
Yeah. And so this curve actually represents how often you get false positives or false negatives. The higher that this curve is, you can kind of see excellent, good, or worthless. So a diagonal line, worthless, because that means that you're basically guessing, like 50-50 chance, nothing.
A lot of bombs out there.
Yeah, exactly. Running around.
I think we use this curve curve sometimes.
Yeah.
Throws a
I'm
bomb.
on a technique.
Yeah, little kids playing Bomberman or something, right? And then you kind of have a good here, which means that you're getting prediction, right? You're above what this would result in an AUC of 0.5. This would be something more like 0.7, and this would be 0.9 probably. And so that would be kind of this area here is what goes into that calculation. And that's the thing that you want to maximize.
So if I correlate that to the like stock trading example, is it fair to say that the people who are really high risk reward are living right on the top of that yellow line? Like they are trading dangerously, right? They may miss a bunch. They have a bunch of false positives, lose money, but when they win, when they hit it, they get up. I filled a lot of tanks and 2 hostages, right? Like I blew up 50 tanks, but I also killed a bunch of civilians. But I blew up 50 tanks. Like that's right on the line there, right? They're really being aggressive. So you want to stay in the middle to kind of balance things out, unless you're trying to make money and you're willing to risk losing money.
Those at the end of the curve have very low probability of being good. But if they're good, but at the end, that means that system gives them like very low probability, and nevertheless they succeed.
Yeah. They get powerful.
All the guys who have high probability are at the beginning.
Yeah.
And the further you get to the right, the less probability is given to this particular observation.
So say you have the true positive rate be 0.7, right? On this graph, you're sitting right there. So that means that you're now accepting a risk of about 0.5 of your false positive, 0.05 of your false positives. So as you climb this, though, you're accepting a higher end rate that you're going to get false positives along with your true positives. And so your true positives up here are basically going to give you. So this is a little bit confusing, kind of out of context, but. So we focus
so much on the false, like not blowing up the wrong tank, but like, what if it's like deciding who should get medicine, right?
Yeah.
Well, you give them the medicine, and as long as it's not some kind of toxic medicine, and they didn't have the disease, well, no big deal, right?
That's the opposite end of the spectrum. Yeah. And so you'd want to, you'd probably be over here in that case because, maybe probably right here. You'd probably be right there in that case because you're talking about. I'll get 90% of the people. Only 10% won't be, wasted
medicine. Yeah.
Yeah, but if you went all the way to 100% and treated everyone correctly, then you'd also be treating everybody. Basically, is what this graph is saying.
So that graph, its context is always against the same pool of data, right? You're running different.
No. Okay, so what happens is, this is kind of, so I've been bouncing around my slides because I'm trying to answer questions instead of going like one by one. What happens is, as we try and do a prediction, we measure how good it is through the area under the curve. But what happens is, as part of the experiment is, I'm going to say, okay, well, I have, and this probably should be something like training and test. And then in certain cases, you'll have validation. So you have 100 records, you take them and you split them up into 50% training data, 25% testing data, and 25% validation data. And so that training data, and ideally you'd do a stratified sampling of that data so that you have an even distribution of situations in the data for each of those groupings. What happens is you'll first train your model to learn your first set of data. Then you'll validate that your knowledge against the data if you have something that's doing micro adjustments on your model. Finally, you'll test against the data. Once the machine learning model sees that data, then your results are invalid. And so you can only test once, because from then on, you have to assume that model now understands that data and will predict it more accurately because it has seen those cases before. And so when we're talking about these measurements, this measurement is, and that offers great context here, but this measurement is taken based on how well we predicted against the test data only. But we use the training and validation data to properly adjust the model to learn the information. And so if you think about the training data is like reading a book. Like, this is the first time I'm going to read the book. The validation would be like quizzes in the end of the chapters. And the test is like taking the test in a class on the book. You don't have the book anymore. How accurately can you predict the information in the book, or how accurately can you regurgitate the information in the book on problems that you've never seen before?
So really, that curve would always be a description of how well our model did against testing.
Yes. Yeah. The ultimate. Yeah. The first time it's seen it. And so you'll take that data. So, for example, and this is kind of where I said in the very beginning, I was talking about how slicing was really a good thing in Python, is because Python makes it very easy to cut that data up. And so you'll have something like a NumPy array, and you can just say, give me a slice, and if the data is ordered in some way and you wanted to do a stratified sampling, you just say, give me every even number, and then give me the first of every 4, and then the second of every 4. And now you have that 25-25-50 split that you can use to do these validations against your data. And so some people are more risky with it and they have smaller test sets, or even, and in production environments, a lot of people just go no test sets. They just go they take all of the data that they have ever seen before, because they're now getting new users that are coming in. So you think about Amazon. Amazon might train it up, probably have a validation set, but then like the end result is that the machine learning is actually predicting what users want to buy based off of what other users have bought in the past. And you might be an outlier, but if they haven't overfit the model, then they will be appropriately predicting for outliers as well.
In the sense that the new customers who are coming in,
they're your test set.
Unknown data it's never been seen before, so it's a valid test.
Yeah. And so that kind of can bring me into my next topic. With that, we have different types of predictions. We also have supervised and unsupervised. And so there are different models. Like if Amazon wanted to real time every new customer that came in understand what that impact had on the model, you can do an unsupervised learning model. And what that does is basically you now incorporate all new data you see from now on into the future. And so the one really simple example of that is K nearest neighbors. And so if you just had actually, we can go back to that link now.
That's how they do they categorize images that are alike, right? They'll do unsupervised learning, just have it sort of say that one's cat-like.
Chris doesn't know anything about that.
No, so a lot of the time image data sets are supervised because they could be unsupervised, but it's a data transformation problem. And so that's a whole other explanation. But part of machine learning is being able to properly prepare your data. And you have to take an image and properly prepare it so that you can interpret the pixels appropriately. And so one difficulty in machine learning, this is what my thesis was on, is that when you have different images, you might have different distances. So it might be the same face, but close or far, or farther, farther. And or you could have it at different areas in the camera. The camera was up here, the camera was down here, here, and here. So like if the camera's up here, a picture of me looks very different than a camera from down here, right? And so in order to recognize that, you have to deal with transformations. Like you have to, and like if I'm looking left or right and things along those lines. So what happens is they get you can accurately predict someone's face in about 300 examples of their face using an algorithm developed by MIT which is called HMax, which converts the image data into something readable by the machine learning system that is agnostic to the position, the direction you're looking, and the distance of your face. And so there are systems out there that can do that, but typically, those are supervised learning. Anyway,
supervised basically just means you're giving some example. You're saying
this is a picture of Chris.
Right.
Yeah.
This is a picture of Chris from here. This is a picture of Chris from here. All these things together are a picture of Chris, and then you give it the same sort of thing, picture of Peter. And it tries to do
so the only difference there is that you'd use one data set and use that model for a long time, and then say, I'm going to retrain it now on more data, where an unsupervised system like K nearest neighbors will be able to basically get more and more accurate as you add data.
So it seems like the supervised system wouldn't have this problem of like you can only test once.
Yeah.
Unsupervised system has that problem because it always learns. And the supervised system only learns when you tell it to learn. So you can test and tweak your model and test again.
But you must always test against data that you've never seen before to appropriately prove that you're not overfitting the model.
But if you've always kept that separate and you've never trained again on that data.
Yes, and you do that same thing with k-nearest neighbors. You can make predictions on data, but you tell k-nearest neighbors to just continue adding to its data set. And so you can kind of see, like, this is an X and Y axis here. And all k-nearest neighbors does is it says, okay, well, if k is 3, take the 3 nearest points and classify it as that thing. And so it does a great job predicting here. And a linear SVM is a supervised learning model that you actually have to run a prediction on it. And so it did a great job doing the prediction here because it actually it took this line and basically made it available. The pink is like low certainty, the red is high certainty, light blue is low certainty, dark blue is high certainty. And what it does is it just takes the 3 closest values and then predicts it. So you can kind of see, though, I have a false positive right here, like the red is not blue here, and here too. So it didn't perfectly identify that value, but if you change the value of k, then this could be very different based on those points that you've seen.
So that creepy thing where Facebook automatically knows your face, like that's a supervised learning thing, I assume, maybe because
it's whatever they found.
People for a while, people were saying,
yes,
this is Chris, this is Chris, this is Chris, this is Chris, and so it was just like creepy and watching that. And now it goes, hey, this is Chris.
Yeah.
This is, and you go, yeah, that is Chris.
That is exactly so. Yeah.
It's the side of Chris's head, and it still knows it. Some crazy way.
But it's kind of a combination of things, right? Because like even like,
and I don't even have a Facebook. I don't know.
Even desktop software can like sit there and say, oh, here's a face, right?
Yeah.
So it can unsupervised just like, oh, there's a face, there's a face, there's a face, and then someone has to come along and tag it to make it known that it's Chris, right? So they're like doing 2 things there.
Well, I know, like, the first thing that popped in my mind when we were saying supervised learning, for a while there on, like, the early Google image searching, they were, like, they added some features that allow you to say, I want to search for a flower, and they go, do you want to search for a blue flower? And it's like a filter, not a search term. You say, yeah, all blue, and it knows that all these images are blue, but it was, like, crowdsourced. They were, like they did it in CAPTCHAs and things like that. They were like, tell me what color this is. Is this picture wrong? And so they were grabbing data like you used to. I want gray cars, and a red one shows up. You go, that's not gray. And so like whatever they were doing there, they were learning and like crowdsourcing the supervision type of
Well,
thing.
there's like, again, all these companies are trying to do as many different things as they can, right? Netflix is sitting there watching what you watch, okay? So, they know that every night you turn on cheerleader slasher movies, right? Even though you're going in there and putting 5 stars on Downton Abbey and Masterpiece Theater, they know.
It's still
So I mean, my Netflix thinks that I'm a toddler, right? It's always
mine's very confusing. You know what's funny? I actually had this. I wrote a user voice feedback for Rhapsody. I've had Rhapsody for like 10 years, and it does your listening history, what music you're listening to. So I would listen, and at this point, I've had it for so long, it has brilliant suggestions for me, right? Because it has narrowed down the scope. But every once in a while, I listen to some terrible pop music, like, Britney Spears' new song, and you just like, okay, I gotta hear it. And I actually sent that. I was like, you need incognito listening button. So I can say, I never listened to this. Turn this on. Don't ever suggest me these things. I need a guilty pleasures button, right? And I just hit it, and then never tell anyone ever that I listened to that song and don't screw with my ratings. They never responded. Yeah, they never responded to me. So apparently they never built. I'm like, come on, this is a feature you need. Netflix needs the same thing. Cheerleader slasher movies should not be in my recommendations.
You can even do a database of creep boys.
See, the problem is when they link my Amazon with my Netflix and my Rhapsody, I'm gonna get arrested probably. His movie and his purchases and his music habits.
They don't want you using incognito every time.
Yeah.
Nope. All right. For some reason, I can't find my thesis anyway, but it's already gone. Dead, so whatever. Yeah. So one thing I wanted to show is just the conversion of that data. But anyway, so preparation of the data is kind of the big thing there.
I have a copy of your thesis, dude.
Do you? Oh, can I have that? Can you send that?
And now
Is your backup?
Yeah. Cloud storage right there. Okay, so a few other things that I wanted to talk about. It's kind of, we probably should get into code real quick, but I like the discussion too. So one other thing that I want to kind of make very clear, regression versus classification. So regression is basically plotting points on the line that occurs, where classification is like this thing is red, green, or blue. And so those are two very different types of problems, and certain models can solve them, certain ones can't. So if you ever look at the sklearn API, you'll actually see that there's there are classifiers and regressors. And so actually, let's go back, classification and regression. And you can kind of see here, generalized models. And so like that, the support vector machine actually has classification models and they have regression models, but some things can't handle classification or regression. So that's just one little thing to keep in your mind as we kind of move forward. Also, certain things are named a little weird. So support vector machines are commonly referred to SVMs, but SVC is a support vector classifier. SVR is a support vector regressor. So you know, just there's like some naming confusion there that got me a long time ago. But you want to keep in mind that those are the two big types of problems, and they explain this in the book too. And we went over supervised and unsupervised. There's also the idea of single model and ensemble models, and so the difference is that if you have a single model, you can just, you know, you have one thing making a prediction. But if you have an ensemble, and a great example of this is decision trees. You can create a decision tree. That's a single model. A random forest is a huge amount of decision trees that have all been trained differently using random values. And what the model does is it tries to get a consensus about the decision. So it's many models making predictions, and then they get a consensus, and that's the final prediction that you get out of it. Yeah.
Is an ensemble always just a multitude of the same algorithm, or could it be like a?
It can be many of other kinds, but it's typically, I think papers are harder to write about multiple models and their interactions with each other. So
they're not worth doing.
So yeah, they're not worth doing. No. So a great thing to look in here. Ensemble this is the whole area of ensemble methods. So they have forest of randomized trees, aided booster, gradient tree boosting, and a voting classifier. So this majority sort of stuff might be what you're looking for. But there are other models out there. So they don't really have a great neural network in this library, but Google had also released their neural network recently, and so that's called TensorFlow, and that could also be used. But the API is much more complicated than this. So two really important things. So let's write some code real quick, and let's work this out. Actually, let's look at an example first.
So these are all examples from the Wiley site from the book. Right?
Yeah, these are the book examples. So let's just see. So pandas. So you have to look at the imports too. So pandas he renamed to PD. So this is like an import statement. You guys have seen that a lot. So
there are conventions here.
Conventions here, yeah, and that's what I want to point that out.
I've noticed that pyplot is always plot.
Yeah, and it's usually it's just a thing, like it just follows the library everywhere it goes. So examples in NumPy, import NumPy as NP, and then you use NP dot whatever. Or people just import star from NumPy, and then your whole system's flooded with NumPy functions. So that, and then also like pandas, they import pandas separately, but they also specifically import data frame. So this happened. I've seen this a lot too.
And why is it called pandas? No idea.
Python analytical data something or other.
Oh, there you go. There you go. You look this up. Yeah. So one thing, I was looking at pandas because I didn't use pandas for most of my machine learning. I have a very low experience with pandas. One thing it does do is time series analysis, like that ARIMA model. That's something not handled in scikit-learn, which is probably why they didn't do those things. So yeah, let's go back to that. And so kind of what we're doing is we're reading the CSV, and then this is the target URL. So this is the abalone data. So actually, look at that, UCI machine learning database. So he's pulling it straight off the website and dumping it in here. And so it's that. Whoops.
Just keep clicking.
I know.
Put the mob timer up. You've been talking too long.
There we go, mob timer. All
Written
right.
in Python, no.
Yeah, that one's written in Python. So
Are you doing background data analysis on how long the mob timer runs? And who's in the mob?
I should be. I should be.
You should be writing analysis.
So I'm doing machine learning on some data I'm collecting at work though, so that's pretty fun stuff.
Please write your last turn at the keyboard.
Yeah, exactly.
Yeah.
What you should be doing is correlating it with lines of code that actually stay in the code base over time.
Yes. Yes. Okay. So that's the project we're going to do for this class. All right. So
Fire the people who find
UCI machine learning, abalone, right?
Yeah.
I spell abalone.
That's pretty close.
So this is the data set that we just downloaded. So we're talking about the gender, the length, the diameter, the height, and everything, and then
Important stuff about abalone.
yeah,
No, they're missing taste.
taste, yeah, flavor. So he slices the data here. So this is the
Slicing abalone.
yeah, we are slicing abalone here.
The jokes are free here, folks.
Yes. I'm pulling that in. Actually, I don't know what this is. You know what that is?
I lock.
Data frame stuff. So this is all pandas. So I don't know what it's doing there. But it's creating a data frame, probably of the correlation matrix. Correlation matrix comes out and it spits out a mob programming timer. Now that you said something, it's always be there.
So much advertising.
And then that's
You
At
should
the
put,
end, someone remind us to explain to you what the mob timer is.
yeah.
so you should put the team members in their positions still available.
Yeah. There we go. So more abalone summary. So they does more stuff in here. Plotting of that data. So this is data visualization, and it looks like he has a lot of different stuff. So then he kind of saves the data. So you can kind of see Pandas also lets you do some cool stuff with, like, NumPy would never be able to interpret this file, but Pandas can, and it writes files like this. So you can just spit out different data sets in the same file, and Pandas will be able to reread it and reinterpret it. So that's another thing, is that you have multiple data sets in a single file. I don't know if that's good or bad, but it's just kind of how it
Well,
is.
sometimes that's what your data is, like
Yeah.
on that data.gov site.
And so correlation heat map, the wine summary. So it looks like he pulls the wine. Yeah, that is the same wine data there. So here's the heat map. And so, yeah, interpreting that is going to be the difficult part. So I'm sure that he'll,
Pretty.
yeah,
Let's
there you
just
go.
call it correlation from one column to the other.
Yeah,
Yeah.
and data relationships and things like that. So that's kind of what he goes through in the first bit. So
He's really just trying to get your head around, like, what types of things you can do on the data and how you can produce the visualizations for the data, but
Yeah.
not really telling you what you're looking at. I've got a cool picture. What does that mean? I have no idea.
So I'm going to do some stuff that's not related to the book, and oops, I'll just go from there. So from NumPy, or import NumPy as NP. All right, and then so for example, let's go grab the iris data, or not the iris data set, the iris data set. So iris data set's the hello world of machine learning. I think I said this before. So UCI, machine learning database, iris. So the iris flower plant, you kind of have 3 different types of data, 3 different types of flower in here, and there are different measurements of that flower. So those, let's see, title, source, attribute information, the length, width, and class. And so this is a classification problem. Can you predict which iris flower you're looking at, basically, right? And so I won't go through the trouble of really preparing the data so much as I'll just go ahead and create a new file, iris.txt.
You're trying to predict the classification based upon the other attributes?
Yeah, so is it an iris setosa, is it an iris versicolor, or is it an iris virginica?
Only popular because there's no cannabis data set.
I was wondering why there is.
So in here, you do this normally programmatically, but I'm a little bit lazy, so right now. So we're going to do this, and we're just going to go in and change the classes to integers. So there's like a one-line thing to do it, but I can't remember what it is. So you can go in and just
share your fancy keystroke you're doing there.
Alt.
Yeah, alt,
drag.
holding alt, drag, and then just type in a number.
Look
So
like an expert programmer.
so 0 is the first one. To do things you can do programmatically really fast. Now we can just load this into NumPy and get a NumPy array. So first thing I want to do is say np dot what is it? Read CSV. What was it? It is, right?
You have the other file.
Pandas.
No, that's pandas though. I forget what the.
So how come you're not getting results in NumPy? Couldn't you do something?
Oh, I think I am. I think I'm just typing in the wrong
Yeah, it looked like it
thing.
was deleted.
Jen from text. All right,
Whatever, I got there first.
thanks. So this thing. So that's NP. So
the reason no one tells IntelliSense is because
You didn't even come close to the right.
yeah, it's just like I have no idea what you're talking about. I am intelligent.
so you can
are
kind of
not.
see it is there. So what happens is NumPy will sit there thinking for a long time when you get a new library. So installing Anaconda, it will take a long time. And then on top of that, when you open it up, when you first set it as the project interpreter, PyCharm is going to take a long time because you'll have a little loading bar on the bottom right. I was like, what the hell's going on? Why is nothing working? And the reason that it's not working is it's actually indexing every single thing inside of Anaconda.
Oh, okay.
And so it's a little bit painful at first, but we can, you get past it. So here we have data, right? And then we say print
Yeah,
data.
right.
Because
Iris dot
you want
text.
to clean the file.
Dot TX.
Thank you. About programming. So you can kind of see it. So I printed out the data that we got. So we now have everything inside of NumPy, and we're actually ready to cut this data up and make predictions.
Cool.
And so
And that's a data frame that it's creating, right?
no, it's not. So data frames, all pandas. So I'm still studying pandas. I haven't really used pandas a lot, but like the machine learning stuff that I've done has all been in NumPy. And there's a lot of cool stuff that you can do with NumPy. So, and the book examples are usually using pandas. So, but he does use NumPy as well. So we'll learn that part together. Yeah.
Can you run out of memory when getting a NP object?
You can, so if you're generating data or reading in data from somewhere or copying an NP object, yeah, you can easily totally hose your system if you wanted
And
to.
the same for pandas, it doesn't store it as a SQL object.
No. So it's not. This is all in memory stuff. And typically, when you're operating against data, you're going to be completely in memory, unless you're really dealing with big data. Big data. The case would be you load some of the data off of it, you learn that data, and then you stick it back. You deallocate it, and then you get some more data, and you run it through, and you deallocate it, and you just run the whole database of the thing to get all those and we'll kind of see that. But this is just that file. I've loaded that file into memory, and it's a NumPy array now. And so my intention now, so we first wanted to load the data, right? Then we want to slice the data into training and test sets, right? So that's and then we're going to train an SVC, support vector classifier. And then we're going to test, we're going to predict the test set values. And then we want to get our AUC and accuracy.
Maybe we should run some statistical analysis on the letters that are missing.
No, that's just a typing thing. It's
Seems to
completely,
be predominantly T's and R's.
yeah, yeah. So, yeah.
Clearly, he hates the R language and refuses to use
Yeah, nice.
This is a stab into its heart. It's stab into its heart.
it. Ripped it right off.
He's still confused with the R.
Yeah,
He ripped
put
it
the
off
G's
his
in and not the R's.
TiVo.
To get rid of the R's in his name.
I'm missing R's. Okay, okay, so first let's get the right, is that right?
Training.
And so we have data, and I'm just going to do a simple slice. So what we can do is the every even row here, right? And so we'll just print that out and see that, right? And so now I have basically half of that data set, right? And later I can shuffle it or something along those lines. And actually, oh yeah, sorry, I printed it up here, and then and one nice thing is we can just see the shape, right? So the shape is the dimensions of the data.
Oh.
And what's nice about this? So we had 150 rows and 5 columns, and then now we have 5 rows and 5 columns. So also we're going to actually want to slice off the yeah, the last column. So that's the classification class. Yeah. So slice class off. So.
Reminder, L is that for long data type? What's that what it is? I was trying to remember from the Python book.
L, where is the L in?
Where
there?
the
results.
shapes-
Fine, now.
Oh.
the shapes are all in L's.
That's gotta be
It's
coming from
it's a data type.
NumPy.
Yeah, well, NumPy is
Yeah,
spitting that out. Yeah, but I believe it is.
So the dot-
Jim's on it.
The dot shape method is in NumPy, not Python. It's not just Python, it's Python object.
That's correct.
Means it's 32 bits.
Okay, good.
NumPy is about types. If you're missing a type, that
So we have a test set of 75 and we have a training set of 75. And it's stratified sampling because it was all kind of in order of classifier, and I've sampled from each one. Typically you use that to reduce the size of your data set, and in big data you'd say, I want to get 100 million records out of 1 billion records, so I'm going to do stratified sampling on the data and then pull that out, and now I'll be able to run a more expensive algorithm to do predictions on it. So
You took off the classifiers off this data set, correct?
No, not yet.
Not yet. So that's our next step. So now we want to just say, so this is train and test shapes. And then up here we'll do data shape. Right, so we can kind of see that. And then now we're going to say train, and then typically what they do is input or train in or train X. So there are multiple naming conventions in data science, but a lot of the time people just use X and Y. I don't like it because it's not descriptive. So then they have train in and train out. And typically I just say train input and train output. And that's kind of what, that's the convention I typically use, but it's not common. So you could do whatever you feel is right. So I can just take the original train data set and then just say that I'm going to do 0 to 4, inclusive, exclusive, I don't remember. And then train output. And then, so there's that T again. Train, and then that's going to be, so that's all rows, and then, last column. Oops, and then this is going to be 0:4. So now we can print those out. train in and out, and then train input. How'd you know?
Sounds like you're tracking.
No,
I love it.
like a man
Love it.
for a job at Hunter.
Yeah, you need a job?
They told me not to quit the day job.
Okay, so what does this tell us now? We now have, that's our shapes. So the train in and out shapes. We have 75 rows of 3 columns and then 75 rows of the 4th column. Do we have 5 columns or 4 columns?
5.
So I lost one somehow. All right, so let's try that again. 0, 3, 0, 4. So actually I can figure this out by testing the output. Whoops. So no, that's right. 0 through 3. Oh yeah. Is that 0 through 4?
Yeah.
And then, yeah, okay, so because this is it. This is inclusive, this is exclusive. So that's what I was getting messed up on. And we can prove that by looking at the data here. So yeah, we have the 4 columns, and then we have all the outputs for those, right? So we can cross-reference all that information. Okay, good. So next, we want to get that same stuff for the test sets. So I'm just gonna be
What is
bad
the
here.
output right now as it sits?
Down here, it's all of the data without the classifiers on it in one array. Train output is this guy right here.
0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1.
Classes for the ordinal position of the data, right? So next up, same deal for the tests. So I'm just going to do the thing where we just say Control H. No, not Control H. Find replace on here. Yeah, but what is the? Anybody got the IntelliJ shortcut for find, replace, and selection?
Is it?
I'm gonna find and see what it gives you.
Yeah, find. Match regex.
Self-destruct.
Yeah, not quite what I want.
R.
R.
Control R maybe.
Yeah, it looks like it'll work. Control R for replace. I got it. Train.
H is way better.
Python's better. Wait.
Replace data.
Hey, that works. All right, cool. So if I run that, and then we put the dot shapes back on here, we can kind of just keep an eye on our data, make sure that it doesn't change its shape. And so obviously there's a lot of symmetry here because I didn't take a different set of data, right? So then, let's see, next up is going to be training an SVC off of that training data set, right? So SVC equals SVC. And we just see sklearn, SVM, SVC. So you can see the namespace that it's going to import for that. So we have a support vector classifier now, right? And we're going to just say svc.train. Fit is the interface. And then, so here's the kind of thing. So train, whenever I say train in sklearn, they're going to say fit. In other systems, like Google system, it's something completely different. Neither of those terms. So you're just going to have to figure out what is the train thing. And then the same thing with predict. sklearn uses predict, but I've also seen Y or output or like all kinds of weird stuff for it. So the APIs for these have been made by statisticians, not by code people, clean coders and things like that. So that's kind of why these things have weird APIs. Yeah, people in Python, they just go all over the place all the time. So
Sorry, take a step back for a second, make sure I'm still following with you. We've got all the data loaded with the iris data set. The goal of this, not me the right term, the goal of this exercise is to see if we can predict the type of iris it is on data we've never seen before. So the first thing we need to do is train the classifier to look at you're looking at 75, half of the record. Right?
Mm-hmm.
Look at these first 75 and learn the first 75. And so where is the
wasn't the first.
Well, every other.
Yeah, it was every other record. Yeah.
Where is the, maybe you're not there yet, where is the algorithm part?
That's the SVC.
Okay.
So
that's just
it's
magic?
this guy,
It's
yeah.
just magic?
So that's why, I mean, that's why I said practical, because this book is a lot of it is just magic. And so you don't do a lot of digging. And we could go into other examples and
So it's gonna take the data, do some magic.
Yeah.
Just say, cool, I know this data, give me some more data.
if we're interested down the line when we finish this stuff, we could dig into and just say like, let's create a neural network or something like that. Because by the end of this, we won't have breached the subject of neural networks really. So
if you are someone who knows all the statistical algorithms that you might use, you would be able to look up on NumPy what the dot fit method actually uses. Does it just use one or?
Well, so we can actually show that right now. So like SVM. So let's just look up a support vector machine here. So support vector machine. Yeah. So great examples of what it's doing. It's actually drawing a line between the data, creating two other lines to kind of declare its certainty, and then it pushes out to the next most nearest point, and then it defines that line, and that's a support vector. So support vector machine creates a number of vectors that slice up the data, and things in between those areas become predicted to be that thing. And so there's this is like a whole series of things, of equations, basically, this stuff right here, that allow you to create the support vectors.
So we created a support vector
Classifier
in NumPy, which by convention means it's using the support vector.
Yeah, it's using these algorithms. And so
there's this whole math algorithm crap they got all put into SVC.
Yeah. Magic.
Yeah.
But
And so
you asked for a certain technique, right?
That's what I was getting at.
Like
How
you-
did we, why did we choose to use
Yeah.
it?
okay,
Yeah,
no,
so you want someone to cut down your tree, you get in here with a chainsaw, get in there with a hatchet. Like, you don't really care how the chainsaw or the hatchet were made, but you do know the difference between the two tools.
yeah. And so so I could have used a random forest classifier, or I could have
Great
used
place to use a chainsaw.
I could have used k-nearest neighbors. I could have used a lot of different things. And so we can try different algorithms now. Once I have this example, we can just switch out the algorithm that we use and pick them. Yeah.
I have two little questions. You had mentioned that we cannot rerun the same engine on the data more than once, but won't we be doing that? Can you not tell the system like reset yourself?
Ordinally in your lines of code is what I mean. So by the time you've trained, if you test against data you trained on, then your results are invalid. Does that make sense? So
because you told what the correct answer is on those.
yeah, so it's like saying this is an open book test and you have infinite time. Like that's basically what's going on.
Definitely get it right.
So yeah, you'll eventually figure it out,
So
right?
that's what you meant.
Yeah, yes.
And then when you finish this coding, we have the answers for the other 50%. We know what normally the type of plant is, and we're going to compare about what it think it should be based upon the dimension of the plant with the actual result. That's how we can see the success ratio.
Yes. And that's kind of when we're going to talk about the accuracy versus the AUC, but they're probably both going to be one in this case because support vector classifiers are very widely used and they're very powerful and fast and good. Like it's probably kind of the default thing that you should go for initially in any case if you don't know enough about the other algorithms to make a decision about which to use.
Support is classified SVC actually also allows you to remove outlier. I mean, sometimes I have a lot of points that are very invalid actually, and I don't want to include them in the these two-line calculation.
Yeah, so there are other algorithms. So if you just say sklearn remove outliers, they actually have an algorithm that you run before that. And so novelty and outlier detection. And so you run this first. And what it does is that you do a fit and a predict, and then you get out a set of data that removes your outliers. And this is kind of, it'll like keep this data set and remove these and things along those lines.
And then you run fit again afterwards?
Well, then you take another algorithm and then you train against that data without your outliers. So so they use the same interface for different things, and that's a downfall of sklearn. Yeah, it's conventions dot fit train the system and dot predict, give me the results. So by the time you predict, you'll get back your results without your outliers, right? But it's the same interface and shouldn't be confused with other things that do fit and predict, like a learning algorithm. So like if you're doing outlier detection, it's different from, even though the interface is the same on that class, it's actually doing something different than like a machine learning model, like a SVC.
So you can run outlier detection no matter what the next out, like if you use SVC or anything else, doesn't matter, it's the same.
Yeah.
You use outlier detection, it blows away the things that are way out of range, gives you a subset of the data that's clean, and then you do whatever you want with it.
Exactly. And there are other examples of algorithms like this, like bagging or feature elimination. So commonly in machine learning, I should back up, a feature is the column basically in these data sets. So if you have, we have 4 features and then a Y value or an output value. And so if we want to run feature elimination, we can actually take this thing, sklearn feature selection, also has the same the same basic thing. So let's see, feature elimination. So feature selection as RFE. I don't know why they called it RFE, or they import RFE, which is the feature eliminator. Then it gets selector, and they call fit, and then now actually support underscore gives you whether or not the feature was used, and then it gives you the ranking of the features. But if you predict, now you have your features without, you have the only the relevant features. And even in the iris data set, this system will actually blow away 2 of the 4 features. So 2 of those things, two of the columns in the iris data set are actually not useful. And the only way you'd know that is to have this computer look at every example and tell you these are actually don't have any correlation to the result.
Meaning that it can predict what iris it is without those 2.
Yeah, and then you can eliminate them.
And what do the algorithms commonly do? So let's say you've trimmed those outliers,
Mm-hmm.
and then you feed it an outlier.
Then it will make the prediction based on the training data that did not have the outliers. So it probably would get it wrong. Yeah, so it just depends. So in big data, you'd say, I just can include all my outliers, but I can't use a neural network because a neural network will take years to train.
Right.
But if you wanted to use a support vector machine on big data, you can sit there and it will chunk through all your data as fast as the disk can read it, and you'll have something that you can operate on. So, or even better, a linear regression model, which is like the simplest but stupidest kind of model.
Couldn't you've trained it to eliminate the outliers, you feed the non-outliers into the training set so you can predict. Can't you have the thing that figured out what an outlier is run? If new data is coming in, can't you run it through that thing first before it goes to the?
Yeah, you can make decisions on whether or not it's an outlier.
Because
you have to hold around the entire data set so it knew what were outliers.
Well, you train it first. So depending on,
you got 2 different systems.
Yeah.
Right. And so if you run them through both, then it can say this is an outlier. I
And
don't even want to guess.
Yeah.
I swear I only listen to Britney Spears once. Stop.
Outlier,
Yeah.
Brad, outlier.
Talking about it.
And so in here, RFE is actually one of the feature elimination systems. And so there are actually different internal algorithms that do different feature elimination.
Yeah, what he was saying, recursive feature
Yeah.
elimination.
Yeah.
It's actually the first line in the documentation.
Yeah.
We don't read that.
Dang it.
All right, let's do some code. Let's finish.
Okay, yeah.
See
So
how
let's
good
get back to it. Okay, so at this point, we've trained it, but there's nothing much else going on.
You were running it. Well, that's cool.
Yeah, that took a while. I'm wondering why. Is it just because we did the fit? Yeah, I think so.
Maybe it was the first time you had run it.
Yeah, okay. So, all right. Okay, so what do we do now? We just say results. I never learned how to spell. I learned all this stuff, but I never learned how to
That's
spell.
autocomplete.
So test input, right? So we're going to predict our test input and spit back the results. Make sense?
And these are the ones it knows the answer to this, right?
No, these are the ones it doesn't know the answer.
Oh, 'cause the first.
And so And we can kind of tell we actually, so
Yeah.
I didn't reorder the data. And so you can kind of tell that here it missed a couple, right?
Yeah.
And so we actually didn't get it all right. And then, but if you wanted to try that other scenario, you can. So you can just say here, we even had false positives based on.
Wait, sorry, what was the difference you just made there?
So I
set it back its own training data.
Yeah, I tested it on the training data.
And it still missed.
Yeah,
Well, that's kind
because
of good. It means he didn't overfit, right? The thing is actually making predictions instead of just looking it up in a table.
yeah.
Errors on training data is not overfitting. It's actually kind of doing, it is figuring out the rule here, and it wants it to be useful. If it predicts all the learned data, like very accurately, the more it is more likely it is overfitting.
And you're farther on that
Not
curve.
necessarily, but it is not. Your goal is not to predict learned data. Well, you know the answers anyway.
Right.
It's like that SKDC, get random number, and it just says 4.
Right.
Chosen by random dice roll.
So when you looked at the results, you said it's not quite right. Like, how did you know from looking at it?
Because we so we have let's see,
Reorder.
yeah, we never reordered. So
It should all be zeros and then all the ones and then all the twos.
yeah. So here you can kind of see this was
Those are the answers. Right?
those are the answers and these are the predictions.
So to finish, you just slap a sword on there and ship it.
Yeah. And so this is now our robot overlord. It doesn't know how to detect iris plants, but it's going to make decisions for our life from now on.
Yeah.
So from there, we're talking about that AUC and the accuracy. So we can just say, what was it?
Man, caffeine.
Yeah. Oh, yeah.
Dying. All right, all done.
All right, we're good. All right, so let's just say sklearn AUC, metrics AUC. So they have there's an algorithm for that. And so yeah, metrics ROC curve, and then metrics.auc. So this is basically the stuff that we want. So Y is the truth values, pred is the predicted values, and POS label is just something Brad put in there, I think.
Yeah. What is this label at the end of this?
So
So is this going to draw us a graph?
no, but we can get into that too. As long as we have time. We have time.
We got as much time as you guys want. But if people start getting up and walking away, that's
Yeah, no, then we're done, right?
our online viewership goes down. We're still good. 12 solid viewers the whole time.
See this? Why is it crossed out?
No, not a single question remote. I've even begged them twice.
Was it obsolete or something?
What is that about?
Yeah, it's probably deprecated.
Yeah.
Deprecated and will be removed.
Well, forget
There was a
that.
different method.
Oh, I'll just try and print this out. Why I have a version of sklearn that doesn't match the documentation. I don't know. Why is not defined? That makes sense. So this is going to be test output, right? That's the real values, and then result is the predicted values. So we can.
POS labels is close to, well, so actually how you do ROC on multi-class.
0.95. So that's a really good AUC. So
Yeah.
our curve is just really good. And then let's see, there's also another one.
Like, yes.
And that's probably because it's a small set of data with only 3 possibilities, right?
Yeah.
It's 1 of 3 irises and you've only got 75 rows. It can't be that hard to get that right.
2.
Yeah, so
Okay. Here goes the math
so
major.
this is actually ROC of.
Thank you, math
class
major.
2 versus class
Yes, yes. Okay, that's a great point. So the label so since we have 3 labels, you can only do the false positives and false negatives of one thing that you're predicting.
Oh.
And so my copy of the POS label is the class that we're attempting to predict that we're evaluating for the AUC. So accuracy you can show forever the whole data set, but if you're regarding classifiers, the area under the ROC curve is based off of only the class you're focusing. It's 2 versus everything else. Does that make sense? So 1 and 0, the classes 0 and 1. We're saying how many true positives and false positives we got for 2.
2 being that type of virus.
Yeah. And then the Virginica.
0, 1, 2. Those were
0 and 2.
Is it a column or is it?
No, saying how.
That really should be blue iris, yellow iris, white, or whatever the iris.
Well,
is.
so that 0.95 was a measure of how accurate it was at predicting a Virginica.
Category 2. Yeah.
How accurate it was. at
Yeah,
predicting
but
an
it's
iris will
accurate is a misnomer. It's the area under the ROC.
So,
I wanna be very-
It all goes back to World War II, you see.
Yeah.
one, we don't want
It does go back to World War II. I just want to highlight that right there.
Can you go back?
We are talking about tank detection here.
So if you were to change that POS level to 1, it would be potentially not 0.95.
I believe 0 was predicted 100% accurately. So, oh wait.
Yeah,
So
0,
to-
0.
So to be explicit, because I haven't heard it yet, is it position label? Is that what?
We're assuming that the
I think so,
transition
yeah.
points are
Okay.
accurate. though.
Because I tried to look out and see that.
Yeah.
I mean,
Let's
the-
prove that
the
out. Let's figure that out
zero,
real quick.
one,
Oh, sure, because we switched, we got every other, and we may have pulled 1 or 2 of more of 1 than we should have.
Yeah.
Nope.
Yeah, for sure. So interestingly, what you just did there was POS label.
Positive
one only was
label?
The label
55%.
considered as positive.
Oh, okay, so
Oh,
positive. label.
Yeah. Again, so how well did you predict
Yeah.
this?
Which ones they
So when you
use.
first
Yeah.
spawn, it says it's 55, you're right in the middle, it's really bad at predicting
That is
1,
bad.
is that what we're saying? It's a crapshoot whether it'll get.
Well,
ones
there
right.
are an awful
Right,
lot of.
yeah.
ones that
Look at
extend
how many
over
times it
twos.
fucking, messed up. 3, 4.
Oh,
Dude, come on, YouTube's gonna ban us now, though, cursing.
do you understand?
Yeah.
I think it was talking about.
CERN just dropped off the feed.
So it'll do a really poor job of guessing.
Yeah.
But if you said, don't pull every other, but pull every third, then it would totally change all of this, right? Like,
Yeah.
because like she was mentioning, we're making an assumption that the transition, that it's even chunks of each type, but it probably isn't. It's
Mm.
probably less 1s, more 2s, more 3s, or whatever,
Yeah.
and we cut it every other.
Find that out.
Isn't there a function in
Which
order
one?
to randomize an array?
Right,
Yes,
shuffling,
shuffle.
that's the thing we talked about.
So-
That way to make it smarter, right?
So we can say here,
After you run the data shuffle?
yeah, data.
If
So
it has a wider spread, it's better at doing better classifying, right?
Right. It would,
well, so the problem is our stratified sampling thing happened here, right? And so before I slice the data here, we probably want to shuffle these, if anything. Oops.
Don't you just want to shuffle data?
No, well, because you want to make sure that your sampling was stratified.
Yes, but you should shuffle one time, not shuffle many times.
Well, the test and the train are now separated. Does that make sense? So
Now they're going to overlap.
You might, but sometimes
Yes.
you may get some data
Absolutely.
in the train into the test. You have to shuffle completely first, and then you can split.
oh yeah, you're right. Sorry. I'm gonna do something I despise here.
Oh, best thing ever.
No, we're not gonna be able to eyeball the accuracy.
Yeah, we won't be able
That's true for the
to.
machines. The machines are always right.
I feel like we just can't change this up. That's what we do.
Yeah, there's the
There you go.
Here you go, boss. This is what you want.
Does it shuffle the X and Y? I don't remember.
You're shuffling the rows, correct? Not the whole thing.
Yeah.
Oh, I hope so.
Wait a minute, you still need to shuffle the data. It's data. You have to shuffle data.
Yeah, I think we've decided that.
Well, he didn't do it.
Yeah,
We decided it, but he's the dictator in this
You need to
situation.
shuffle the
And
entire
he just
data set
overruled
That
us.
doesn't help.
He random shuffle.
You need to perform stratified sampling. So unless you have a good way of doing stratified sampling, so you could shuffle it all and then it will be random every time. So we could do that. So first let's try that one out. Let's see.
You're shuffling after you load it. You cannot shuffle it after
Well, let's shuffle first and then
you
take care of the
cannot
other
shuffle
one
it after you split it.
You can, it'll just have no effect.
then.
You're correct.
Well,
The whole
no,
idea is you don't have
the
that-
order in which you receive the rows that you train do affect different algorithms.
Yeah, that's
So
Yeah.
so shuffling it every time is actually a good practice. So
Thesis is like this big.
Okay, but
but
we don't know if this.
I need to make sure that
It's true. I get that.
np.random.shuffle is what we want. What is the blue box that I'm getting here? Is that narrator?
Probably, yeah.
That narrator, that jerk. I don't even see it. Okay, anyway, I'm just gonna ignore it.
It's down there. It's got a talk bubble. It's next to Microsoft Word. It's probably narrating for the people on the Hangouts. If you want to put, is that what it is?
normally
Thanks.
we should be adding to every row a key so we can compare them.
That's what the.
All right, so where are my shuffles here? So np.random.shuffle is what I want, and it will shuffle the rows. Otherwise,
so
I'm
we
going to
had-
shuffle everything.
100% accuracy on zeros, 55 on ones, and 95 on twos.
Oh, that's not accuracy. It's zero.
That's all right. Thank you. Thank you.
See, it all goes back to World War II.
The thing is, you don't want to accidentally miss your hang.
I misspoke. I meant that. Sorry.
Where did
Well,
shuffling?
accuracy is it's kind of dirty word. Machine
Let them finish this thought.
learning.
Stratified sampling.
No. Yeah, I get it.
Let them finish the thought, and then we can try to prove it wrong.
It's because it's harder.
It's harder.
No object
What's harder?
shape.
Shuffling first.
None. I guess my little trick didn't work. Why isn't that
And you
working?
despise.
It might be,
Yeah, it's just killing me inside, I think.
I think it's shuffling in place.
Oh, no, it's
It
shuffling
does
in
not
place.
return anything. So you do not have to do the thing you despise.
Yes. Winning. All right.
So same.
So there you
So SVC is not one of those algorithms.
Oh, hang on. Let's try the other 0 and 2.
So let's just try this a couple times.
Same
95, 95.
Yes. SVC is not one of those algorithms that.
That cares.
Wait,
Well,
Yeah.
it's not different.
Yes.
It's a solid one.
Yeah. So let me see. Random forest would be a good one to do. So SK
Let's go back to
learn.
this whole shuffling thing because we have some staunch disagreement in the front row.
Okay. All right. Let's start with that. Okay. So
Yeah. So humor us
and shuffle that, right?
and shuffle data.
Before you.
Yeah.
Right, that's.
You want to do that before you split it into train and test.
Right there. You're a good mobber.
Coming out 16 and 17. Now you've really done it. You shuffle. You don't want to shuffle.
Hey, look, 98.
You got better. 97.
Of course, we shuffled all of data anyway, so we can't eyeball it at all. But I mean, it's basically going to
Try
be different every.
one.
Right. Yeah. That was still 2, which was 95. We're getting
Consistently
a little bit better.
Yeah, it's not 99.
Now 1
It's worse.
worse. Oh,
Better.
there's 1.
Yeah, 59.
Worse.
So this is the trouble. So in all of my machine learning classes, we ended up doing this. Is like, okay, give us back your accuracy or your AUC, and people would just run it over and over and over again until it was really high, and then turn that in as the results. So yeah. So and I mean it's super common. So like you'll read in papers that are like, oh, we got this number, and it's like magically you try out the experiment that they had in their paper, and it's like way lower until you rerun it over and over again. So
Will I be president?
Yeah. So
Statement of.
and what they do instead for the experiments now is they actually write a thing where they rerun it 5 or 6 times and then take the average.
That's good.
So that ends up being kind of like, because the random in this is going to always be hitting you. So
let's call it like 10 more minutes.
yeah.
Or less.
Actually comes from statistics.
Yeah.
It's like the data set that Fisher was very fond of. And so in classical statistics, when they had like data sets with 5 records, they brought all the complex mathematics. How many observations do I need? Do I see? Do I have enough to support the hypothesis? What is my confidence interval? All that.
Yeah.
And machine learning comes from our age of computers. We have a boatload of data. If you have not enough, okay, we have even more over here. So we just drop we can throw more stuff in. So we don't have this kind of issue that, yeah, it's 75 records. What do I do with 75 records? Anyway.
Right. I gotta know what kind of iris I'm looking at. That's why I gotta take a picture with my phone.
Most recent one is in genetics, where we had like 10 people sequenced and we spent millions. But nowadays.
Because of the data. There's a finite set of data there.
Yeah,
You know,
it's
only
there's not
150
enough
values, not enough.
So if you, so say you try and you give it more data, right?
No,
But it's the type of data in there.
Oh, it does actually.
It's evenly split.
A data set contains 3 classes of 50 instances each.
So evenly split. 50-50
Evenly
split.
split.
But there may be overlap in some of the characteristics.
Exactly.
Right.
There you go.
So
One class is linearly separable from the other 2. The latter are not linearly separable.
well, I was gonna say, class 0 is probably linearly separable.
You just
You
use
can-
really
that's
big
why you
words,
give
so-
I can't even pronounce these words. There's too many
I
R's.
knew what that meant.
Take it out.
I program in R.
So that's the one that was 100%. So
Right.
You need your tests to be studying it too.
Hmm.
You've got your train for 0 and 1, shouldn't test be studying it too.
Yes. What exactly happened there?
Now we're getting to the point where the machines are just killing.
Yeah. No, it's not append.
So
Are we
Concatenate.
certain that the shuffle, there's a row-based mix, not the whole?
It is a row-based mix, so that was why I
It
switched.
would be chaos.
Yeah. We're
We're
getting
zero.
We're really close to the
So
same values every time.
you gotta,
So really have to be-
It's this guy that's doing that. So if you used random.shuffle and not numpy.random.shuffle, it'll shuffle everything. And so you want numpy's shuffle, which shuffles just the rows.
So you did a row-based shuffle on the entire 150 record data set or whatever it was, and then split it and trained it, and you got different, every single time was a different result, but when you split it and then shuffled the split, you got the same result.
Yeah, meaning that order does not matter within the algorithm.
All right, one last thing. We're going to do a numpy v stack. And then gives, so we need a tuple here. Every once in a while, I see a lot of this where you have to have a tuple of an input and it looks confusing. So now what I did is I gave 66% of the data to the training set and only took 33% of the data for the test set.
Wait a minute. 0?
So I think 0 is it's 1. I'm not really sure why.
Okay, right, okay.
Perfect. Yeah. But we printed out the results here, right? So 2, 2, 1, 1. Yeah. So it's like
95
yeah. So yeah, 1.0. Here's the good stuff. This means that label 2 is predicted accurately every time, and does not have a situation where you could get false positives. Basically, true positives.
You should shoot that thing to tank.
Yeah, you can shoot the thing in the. If you ever see a 1 on an AUC, you have a perfect model. You can go to the bank with that. So, or you massively overfit the
We'll
data.
start our iris prediction.
There you go.
We only know about 3 irises, but we'll get it right.
Yes. I'll put this code on GitHub.
So, interesting. So, do you open your iris.txt in?
Sure.
Let's say we were to just
turn off the lights and my iris. No.
let's
I got a
laugh.
laugh.
We have 0, 1, and 2 as the 3 irises. We could add 3, right? Randomly.
Yeah.
And then rerun the same thing.
So there's also noise experiments, and so one thing that I had in one of my projects was to create artificial noise columns and add them into the data set. And our feature elimination is supposed to be able to detect that those are artificial noise and eliminate them.
So it wouldn't, Scott said to mess it up. It wouldn't so much mess it up as it would introduce a new iris which you know about, so the availability of data you know about.
Oh, yeah. If you predict, you won't predict.
Values, like a 5.7 and a 3.0 and a 1.2.
Well, that just means that it's
and then
ambiguous.
Say it's a 3 now.
Yeah, it's
It
ambiguous.
will
It
mess
would get
up.
worse. It would get worse. Right? It would intelligence would be into it.
Well, so
It's ambiguous.
yeah. It becomes, if you use that, the whole rows from there, and then just split that data set into
Right.
2 and 3, it is ambiguous, and the AUC will go significantly.
You would have to grab a whole chunk and change every number in the column.
Yeah.
Well, not just every number, you have to change them in a way that there's no overlap, right? Like you can't even say, I'm only going to use numbers with 2 decimals, 5.45 and 3.96 and 1.32, because they're overlapping in between 2 values that would ordinarily have the same classification, and now you're putting something in the middle that doesn't.
That introduces a really cool thing, though, because you have decision trees. What decision trees do is they actually base the next decision to be made based on an entropy of the value to the accuracy or the value to the AUC of the results. And so,
order would affect.
Yeah, and it would change how that tree is shaped. And when you look at the tree in the end, you'd be like, oh, these are ambiguous. You'd be able to spot it right away. What's up?
So we're doing some of this type of things for fraud calculation, or fraud analysis, fraud detection.
Sure.
And we're trying to basically label the vectors of a non-fraudulent events. You know, so I work for Wells Fargo, so as customers do this, and that, that's all good, because we got billions of transactions. We're basically trying to identify the hay, and then filter it out, and that way the needles will show up, and those are the fraudulent events. And so I'm trying to figure out, to do this, we're basically determining which one of these guessing algorithms that we're going to use against the data set until we get.
Yeah, it's a statistical thing. So like different algorithms will get you different so it really depends on your data. So what a statistician would do is they go in, they try and understand each column in your data, and then pick an algorithm that they think would work really well. Or you know, somebody else might go in and just guess at which one of these algorithms they'd want to use. But you can kind of see that all of this data is shaped very differently. And this is just a 2-dimensional plane. But so these models work on a hyperdimensional field, meaning that you could have a 30-dimensional space that you operate in, and then these just have linear algorithms or forests or whatever. But like a linear algorithm in a 4-dimensional space will, you know, you ever see a picture of a 4-dimensional sphere? It's like represented in 2D. So the idea is that you will draw a line, a hyperdimensional line through that data, and especially with support vector machines. Once you draw that line through that data, so this is only 2-dimensional, but it could be 20-dimensional, and then that line will now determine whether or not it is fraudulent or not, right? So like the red and the blue here is a great example of that.
So let's I'm too dumb to understand most of what you just said, but in a very simple sense, Dave's trying to find a fraudulent transaction.
Yep.
If he just used what we just wrote, right?
Yep.
You would grab a set of data that had one column that marked it as fraudulent and all the other traits about that, all the other features about it, right? And you would run it through there, and you would say, here, I'm going to train it on this data to tell you which ones are marked as ones that are fraudulent and zeros are not fraudulent. And then it's going to give me a AUC to tell you how well it thinks it will do at guessing whether the next transaction is fraudulent based on these features that transaction has.
So specifically, like for Wells Fargo, what you'd want to do is
Chris Lucian never does
is calculate the ROC curve. And so you're not worried about the area, but you're worried about you're worried about true positives versus false positives. And so if you don't want to be accusing your customers of fraudulent charges, so like that's the thing is like I get a call from my bank saying, oh, your card's been disabled, or I'm at Starbucks and it's disabled, but that's because I took a trip to Seattle the other day and it detected as so customers get upset. So there's 2 situations you could have.
They're more upset if don't find
the fraudulent charge. That's true.
Actually bought it.
So you might be all the way up this line on the curve, and you'll be trying to get 100% of the. So the curve might look something different. So let's say.
Well, the decision about what to look for is going to be based on whether it's cheaper to recover the money or cheaper to deal with the pissed off customer, right?
Yeah.
So it's like, I'm mad because you called me too much. Here's a toaster. Shut up, right?
Oops.
Toaster oven, and I'd be okay. If it was a toaster.
All right. So.
Sorry. Weak.
So one of the
So-
biggest problems is decide which algorithm to use.
This sort of thing happens a lot. And yeah, so you're going to run experiments. So you might have an AOC curve that looks like this, right? And so right here might be the sweet spot of people that are going to get pissed off because of your false positives versus, which is this line, versus people that get the true positives and you actually save the money. So,
but we also have like, go ahead.
Is this a very simplistic way of looking at it? Because I'm just starts thinking of more than one vector. I mean, we're talking about customer sentiment of being pissed off, but we're also potentially dealing with the amount of loss. You know,
yes.
right? $2 isn't worth caring about, but 2,000 all of a sudden we use.
Yeah, and so that's you might have thresholds. So like, so if you have a fraudulent charge for $2, you might be down here. But if you have a fraudulent charge for $10,000, you might be over here. And so the idea is that you might stop, and that happens to me too, right? Like I'll go and spend $10,000, right? And it just blocks, right? It just blocks the transaction. So I went to the Apple store and I spent $5,000 on a new setup, right? They'll just block it right away. Like that's just straight up out of nowhere. Yeah, exactly. It's like you don't even have this money. But
so like they know that if you went to the Microsoft store first and then the Apple store, it's definitely fraud.
Then there's definitely
nobody would do that, right?
So anyway, the point being that you would use different thresholds on this curve to identify your false positives or not. And so, but in general, you'll want to calculate that curve and then make decisions based on that curve. And each of these algorithms could actually have different. So you'd want to run first feature elimination. Then you'd probably want to run data normalization, and then you'd want to run support. You'd want to run a machine learning model on the data, calculate the ROC curve, and then make decisions based on the dollar amount of the transaction, whether or not where you want to be on that curve for the prediction.
I mean, some of that would be like the feature elimination would be the course grain stuff, right? Like if you know you're never even going to care whether someone sells, that has $2, you just draw all of them. Like clump them all together in $50 or more, and maybe even between $50 and $1,000.
But to me, the really
you could be over here, and you would.
Yeah, maybe it's $2.
So you might be over here where you just pick the no false positives, right? You put the $2 transactions in the no false positives.
Maybe it's not $2. Maybe it's a percentage of that customer's bank account, the average balance.
Yeah.
But really, does anyone use a $2 transaction for a credit card?
Yeah, but also you
A lot.
So
I
those
did a
actually
lot.
become Apple.
All the time.
So the vending machine
Yep.
at Illumina, 50 cents.
Well, and actually the only
Apple.
You don't have to
time-
send it a few times, they
No, but
recognize.
Yeah, I know. That's why I always use his card to buy my soda.
The only time that I've actually had legitimate fraud on my card, the first transaction that triggered the fraud was a $1 authorization check at the iTunes store, right? It says, let me check. And most companies will run $1 just to see if it's a valid credit card number and then reverse it. And so they do that, right? And that's like the indicator. Like, oh, if you get one of those, then you're about to get $7,000 in charges in the next 24 hours. And so maybe those do matter, right? The dollar charge does matter.
So you lose confidence if you can still want.
Well, so it depends on how you organize your data too. Like you might have a data pre-process that says, was there a transaction in the future for this customer for $7,000 when I receive this $1? Okay, those match up. I'll get like you'll add an extra column and you'll say like a 1 at the end. That's now a new feature for that data. So there's data pre-processing, data meshing and stuff like that.
We've been talking about excluding outliers, but outliers can sometimes be the bad actors.
Yeah.
Here's all the good actors all look alike.
Yeah.
This
So you don't necessarily want to run outlier elimination. So you'd want to run feature elimination to make your processing your data a lot faster and make the system just run faster. But you wouldn't necessarily want to run outlier elimination unless you didn't care about the outliers.
And would you do like Bill was saying, would you actually cut up the data so there's 4 or 5 different data sets, you attack it from different ways? So you don't run the algorithm on the whole thing. You just say, I'm going to look at these 3 features so it can be smarter about detecting fraud, and then do that at different times for different sets of features, and then maybe correlate out of all of these, which one.
Ultimately, you'd want to run multiple experiments and come up with a hypothesis and figure out what you'll get out of it, and then you'll just calculate the AUC, and then with those experimental results, you can create a theory about the data, and you can put that into production using that theory.
So right here, we were looking at 4 or 5 columns, and even if we had 100 columns, these to me are a linear attribute set.
Yep.
But in reality, when we're dealing with a bunch of rows or transactions for a particular customer, and each customer is different, how do you deal with that kind of time series?
Thank you for asking.
Oh.
I don't have the answer, but that is what I've been wanting to hit that point.
Yeah. So one way to deal with that is through aggregates for customers. So that could just be something that you run an experiment on. Can aggregates for this customer prove anything to me about that customer? That's one thing. Another option is to denormalize your data and run it on that, and then treat certain behaviors in a certain way.
What do you mean by normalize, denormalize?
Denormalize. So a customer has a bunch of information, and then they have a number of transactions. So that's like normalized data. You have 2 tables, customer table. So like thinking in database terms. If you denormalize that data, you turn it into a flat file. You repeat the customer information for every single transaction.
What's the standard definition of we just wanted to make sure we're on the same page.
Right, but the 50-cent drink is normal for him, but the $5,000 Apple stores are normal for you.
Yeah, and so you can, so in your features, you can still have classes, right? And so a class would be an example of your individual customers. And so you could say, this customer belongs to this class, or a group of customers with similar behavior belong to this class, and that class is now a feature in my input data, and your predicted results will transfer over
So
to.
you're going to just end up bucketing customers or tranching.
You could.
That's what classification is. I mean, you classify based on the amount.
Oh, you can. So your classification, the class you're trying to detect, is the charge fraudulent or not, but you're definitely going to either bucket or pre-process data in such a way. If you think about how Amazon predicts what you want, it's because they find similar customers to you.
I was going to say, you don't have to do that, but in all probability, bucketing will improve the accuracy. Like within the bucket, the accuracy is much greater than if you look across buckets, right? So that's why you bucket.
And it depends on just how. So obviously, Wells Fargo is going to want to spend more money running experiments to properly identify these things than other people. So you might have these different situations, you try them out, you get different AUCs out of it, and then you can prove to somebody, you can show empirical evidence that you have a different false positive or true positive rate for predicting fraudulent charges.
Something we got.
Yeah, there you go.
You have some fraudulent money too. Okay.
I'm just talking about spending time. Like, so you can run machine learning experiments, and it's just like network security. Like, you could spend an infinite amount of money on it, right? And so some companies will be willing to spend more on getting better predictions than others. So like there may be data sets where it'd be great if you just had a 75% accuracy on prediction, right? Like that might be just good enough. And that, I mean, I could just say, okay, let's sneeze out, and okay, I'm going to try a support vector classifier, random forest classifier, and I'm going to see which one does better, and I'm just going to put that into production. So there are situations.
Okay, sorry, I don't want to ruin it. We don't want to blow all of the content in one meeting, so I think we'll have to kind of
this book is going to say a lot of what we said.
We'll hang out afterwards. You guys are.
So just go ahead and tell your boss that the problem will be solved in 1 month, because at the next meeting, Chris will have it all worked out.
So one thing we didn't touch on yet. Let's talk about the little contest thing we were thinking about doing.
Yes.
And then so we have some take home. So the other part of take for those of you that have been here is we all have to take home homework, there's some reading and some exercises we want you to do, so that next month you come in and have a lively discussion. So let's talk about that and then just wrap up.
How many pages are in the book?
A large portion.
You have to read Chris's thesis. It's actually thicker than the book.
Fine.
I
don't know. I don't know. I think my thesis might be thicker than this book.
Yeah, just read every other page.
Every other page, yeah.
Pretty sure.
Number of pages in the book.
That's 300.
So
So we usually
about 300.
roughly a page, 100, maybe 100. If there's 300, we're probably going to go for 3 months.
The first chapter doesn't have any like actual code running in it.
But this book is probably dense. That's the thing I was thinking about. Like,
Yeah.
content is probably dense, so 100 might be a lot to do.
So each chapter seems like 50 pages. No. Chapter 2 is like 100 pages. Chapter 2 is 75 pages. So probably just do chapter 1 and 2 at first and then decide later.
So we're basically trying to understand the concepts of machine learning here and how to implement them in Python, not necessarily to learn all the statistical algorithms behind it.
Exactly. So I want to stay very practical. The book gets into that a little bit, and they actually say in the preface of the book that having a statistical background will be easier to get through it, but it's really, you can ignore that because it's not nearly as complex as the other book. And the other book really, for the class that I learned about that other book in, we basically had to one by one calculate each calculation inside each neuron of the neural network and find the values that it came out with and do a whole run through of a neural network by hand. And it was atrociously long. And so we're not going to.
Software to do that?
Yes, absolutely.
So we're going to say chapters 1 and 2.
Yeah.
Between from now until the next meeting, and then we'll talk about the other content.
Yeah. And chapter 2 does have code that you can run for it, and the code is online in one of those links, and it's said in the book.
And
the contest.
Chapter 1 and 2, how many pages is that?
75 total, or it's not too bad. So because chapter 1 is just reading and basically covering what we talked about here, and then chapter 2 is digging into the meat of it. So an idea we had while we were talking about setting this up is to pick a data set and focus on it and have everybody try and use different algorithms or different systems, like maybe sklearn versus TensorFlow or whatever, or write your own or whatever. So the idea would be to take a data set that is complicated off the UCI machine learning data set or the government data sets, and come back, go ahead and write an experiment, get the AUC back, and compare the AUCs between different people in the group, and then talk about results. And you can incorporate stuff like feature elimination, outlier elimination, things along those lines, and come up with your own solution for it.
Yeah, so we wanted to pick one data set, so everybody is working on the same data, so that when we evaluate the differences between the algorithms, we can see. Now remember, it's not an accuracy thing. Everyone's going to get different answers, and they may all be correct for the question you're asking. And so
everyone's a winner.
That's right.
Everyone's a winner.
How are we determining said data set?
So I figure we could go ahead and, there's enough stuff to focus on until next time, but maybe everybody can go through and look at the data sets, and if there's anything that's really interesting to them, bring it back, and then we can just talk about.
Say democracy.
Yeah,
And
democracy, something.
It's a fake democracy. Make them think like they're guessing, but we'll override them.
I know which one Brad's gonna pick.
Yeah, why?
Adults.
Yeah, I'm wondering. Can we actually watch that?
Whether you're an adult or not.
Yeah, whether you're an adult or
Yeah,
not.
take your job.
So
Not what you would.
yeah.
Right, so read the first 2 chapters and figure out a data set and
Yeah,
do a little experiment.
So look at the government one. Look at the 2 links that are up there: the government one and the UCI
In
machine
your
learning
reading,
repository.
when you're doing the first 2 chapters, there's code samples, and you're going to need data to run them against. So just try some UCI data sets, try some data.gov. In between now and then, use the Meetup discussion tab for communication with us. So post, and everybody in the group can post, and maybe start a thread of, when you start, I like this data set because I like this data set, kind of get a feel for what it is, and the next meeting we'll pick one.
I have a lot of fun using the same data set.
Yeah, well,
Just scrub that for us and provide that here. Give us the reach, and then, from a
Save
meeting.
time, it's done for free.
How about Ashley Madison? There we
So
go.
that is free. Thanks very much for coming out. We'll see you next month, same
Thank you.
place, same
Very good.
time. And
Thanks.
it'll be on
Yeah,
Meetup.
thanks.
Thank you.
Good time.
Higgs boson
Yeah.
data set.